Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, greatest common divisor traversal. So definitely a hard problem today, but it's pretty interesting. We're given an integer array of nums, and we are allowed to traverse between positions in the input array. But we can only do that if the values in those positions share a common divisor. And that common divisor, of course, has to be greater than 1 because any two integers share 1 as a common divisor. And I'm going to be referring to this as a factor in this problem. I just think it's easier to say, and I just prefer that word over divisor. Our goal here is to determine if for every single pair of indices in nums, there is a way to traverse from there to there. And if that's possible for every pair, then we return true, otherwise we return false. So quickly just looking at this example, do 2 and 3 share a common divisor? Not really. What about 2 and 6? Yes, 2 can divide 2 and 2 can divide 6. So they share a common divisor. So you can think of it as 2 and 6 are connected in a sense. And does the direction matter? Not really, because if they share a common divisor, we are allowed to go from 2 to 6 or from 6 to 2. Even though they kind of worded the problem where we're checking for every I, is there a path to j? That's what we're trying to determine. But if there is a path, like in this setup, they don't specify which I or j is greater. So that's how I know that the edges can be undirected. So this is what we have so far. Now, what about 3 and 6? They share 3 as a common divisor. So we know for sure that 3 and 6 can connect to each other in an undirected way. We see in this graph, 6 is redundant. Why is 6 showing up twice? We don't need to do that. We can actually do this. So this is basically to convince you that this is a graph problem. So one way to solve this problem is to build the graph itself and then determine if there's only a single connected component. Because like I said, we can go from 2 to 3, we can go from 3 to 2. The order doesn't matter. If we have a single connected graph, then by definition, we will be able to satisfy the problem because there will exist a path from any I to every j. How are we going to determine if we have a single connected component? Well, it's pretty similar to yesterday's problem. We could do a DFS traversal. We could build like an adjacency list, do a DFS or a BFS. I'm going to do union find, I guess, in this problem because why not? Let's switch it up a little bit. And with union find, the way we would do it is build the graph itself. We will first start with a bunch of disjoint components like this, 2, 3, and 6, one for every single value in here. And then we will connect them. Well, in this case, we start with 3 components. If by the end we have just a single component, meaning they're all connected, then we know that we will return true for this problem. Otherwise, we will return false. There's one more catch here. I've drawn the nodes with the values. Technically, it's possible we could have some duplicates in the input array. I'm pretty sure maybe in the fine print it says otherwise, but I think we can have duplicates. So when we actually build this union find data structure, we will actually use the index of each value. So something like this. Even knowing this, even knowing that it's a graph problem actually isn't enough. We will get time limit exceeded. Because now what we can do is iterate over this input with 2 nested for loops for I and then for j. And then for every single pair, we want to determine, do they share a common divisor that is greater than 1? I won't go in depth into how we can do that, but that is a roughly log n algorithm where n is one of the values from the input. So this solution, as you can see, the nested for loops are going to be n squared, and then to find the common divisor is going to be log n. So this actually is not enough to pass this problem. The optimization that we're going to make to this is going to be very mathematical. It's going to rely on the nature of factors. Specifically, let's talk about something called prime factorization. And I'll do my best to not just give you the formulas, but to actually explain the intuition of exactly what we're doing. Prime factorization is basically taking every number and splitting it up into its prime factors, as the name kind of implies. So for 2, the prime factors are 1 and 2. For 3, the prime factors are 1 and 3. And for 6, the prime factors are 2 and 3. The idea is that if there is overlap, like if these two numbers have a prime factor in common, then they definitely have a factor or a divisor in common. And since we are ignoring ones, we are not going to look at that, but we can see 2 and 3 don't have a prime factor in common. But 3 has a prime factor in common with 6, and 2 has a prime factor in common with 6 as well. Therefore, they share a common divisor. The concept of greatest common divisor here is misleading because we actually don't care about what the greatest common divisor is. We just care that there is a divisor greater than 1. If we were to look at a number, suppose 32, you can think of it as having a bunch of factors, can't you? It has 2, it has 4, it has 8, it has 16. It has a lot of factors, but when you actually take these, they boil down to 2. Like you can take 4 and then split it up into its prime factors and it's 2. You can take this and it'll be 4 and 2, but that 4 is going to be a bunch of 2s. 16, same exact thing. So 32 only has a single prime factor of 2. Well, I guess if we're counting 1 as well, but it doesn't have 3 as a factor. It doesn't have 5. It doesn't have 6. Because imagine if it did have 6 as a factor, that would mean it would have 2 and 3 as a factor, but we already know it doesn't have 3 as a factor. So this is the idea of prime factors. Knowing that, what we can do is basically do this exact thing here. Go through every number and determine what its prime factors are. So we will have to iterate over the input. We can do that in n time. And to get the prime factors of a number, I'll just tell you, it's going to be square root of n in the worst case. And this is pretty much going to be the time complexity of the solution. There isn't going to be anything else required. And let me now tell you why. Because what we're going to do is, let's say we start with 1. We get its prime factors. Again, we ignore 1. So here we will say that we will map a factor and it maps to 2. We know 2 has a factor of 2. Next, we will go to 3. We will again ignore the 1. We'll see that 3 has a factor of 3. So far, there isn't any overlap. There aren't multiple numbers with this factor. There aren't multiple numbers with this factor. But now when we get to 6, we will see that 6 has a factor of 2 as well. So we can think of the 6 being here. And what we're going to do is, okay, take these two numbers and merge them via union find. So 2 and 6 are going to be merged. Generally speaking, I won't go in depth into this, but union find operations, we can optimize it in such a way that they are practically constant. I cover this, I think, in depth in the advanced algorithms course, so we don't have a ton of time to go over it today. That's the idea here. We also will find that 6 has a prime factor of 3, so we'll put the 6 here as well, and 3 and 6 will be unioned as well. Now, imagine that we find another number at some point in the future. Suppose it's an 8. We find that 8 has a prime factor of 2. Do we now need to merge the 8 with the 6 and then merge the 8 with the 2? Because that would not make this very efficient. That would kind of make this the n squared solution we saw earlier. But no, we don't. We assume we have that 2, 6 component from earlier, and now we just take the 8 and merge it with that component over here. And so that leads us to realize we actually don't need to store a list of elements here. We just need to store a single element, and probably the first element we have here is sufficient. We don't need to overwrite it. So if we have the 2 here and the 3 here, that's enough. So we would merge the 2 and the 6. We wouldn't add the 6 here. And then next time when we find the 8, we don't add the 8 here. We just merge it with the 2. So something like that. And we know that a 6 also goes here. So we would take 3, which is by itself, and then connect it with 6. So this can be built pretty efficiently like this now. And as long as we keep track of the number of components we have, by the end, if we just have a single connected component, we would return true. Now we've covered pretty much everything except how are we going to get the prime factors of a number? And I mentioned that we can do so in the square root of n time. How is that possible? Let's quickly go over that. Let's consider a number like 32 for a second. The brute force would just be to iterate for I from 2. We don't start at 1, we don't start at 0, because remember, we want the divisor to at least be 2. And then we go up until 32. And then for every one of these, we check, is 32 divisible by I? Is that equal to 0? But there is a shortcut actually we can take if we want all the prime factors of this number. First of all, let's just list what the prime factors for this would be. Well, let's just list the factors in general. 2 times 16. 4 times 8, 8 times 4, and then 16 times 2. One thing that we kind of realize, and actually I'll change the example to 16 to make it even more clear. We have 1 times 16, again, we ignore the 1, so I won't even do that, but we'll have 2 times 8, we'll have 4 times 4, we'll have 8 times 2. What you'll find is that there's a certain point. At this point, 4 is the square root of 6. Any additional factor that we get beyond 4 is only going to result in duplicates. Look, we have 2 times 8 over here, and next we're going to get 8. Technically, 8 is a new factor, but it's kind of repeated down here. So that's the reason why we only go up until the square root cutoff. Even in doing that, if we see that 2 divides 16, we know with 100% certainty that this is a prime number, because if it was not a prime number, let me show you what would have happened. What we're going to do when we reach the first factor of 16 is we're going to add this. We're going to say in that map that we had earlier, we're going to say, okay, 2 is the factor and 16 is the number with a prime factor of 2. And then we're going to do something kind of clever. We're going to take 16 and divide it by 2, because first of all, we know 2 is a factor of 16, so it will evenly divide 16. And we're going to do that once, and then we're going to do that twice because we can. Why not? Then we're going to end up with a 4, and then we're going to do that again, 4 divided by 2, and now it's all the way down to 2. Why are we doing that? Because we are trying to only get prime factors. If we didn't do this, if we skipped this step, the next factor we would get is 4, but 4 is not a prime factor. We know that because 4 has a factor of its own. I guess we haven't really talked about what a prime number is, but basically a prime number, such as 7, is a number that doesn't have any factors outside of 1 and itself. I'm sorry that I didn't really go over that at the beginning. Hopefully you already knew what a prime number is. So basically now, if we were to reach a number like 4 that is not a prime factor, it's impossible, because we know that 4 has a factor of 2. And if 2 is a factor of 4, it's also a factor of 16. And we just basically canceled that number out as much as we could to make sure that this would never show up. This is one explanation. Let me kind of show you another explanation of this. I'm just writing out a few prime numbers. Let's say 2 times 2 times 3 times 5. I don't know what number this equals. I guess it's 4, 3, 5. This is 60. So we have found the prime factorization of 60 here. We're going to go from 1 up until the square root of 60. We know that eventually we're going to get to 2. We're going to find that 2 divides 60. So what we're doing is, this is just math. This is just basic math. This number is equal to 60. So we got to 2, and now we're just going to cancel this 2 out, because we don't want 2 times 2, which is 4. We don't ever want to consider that as a factor of 60. That's not a prime number. So we're just canceling that 2 out as many times as we can. Eventually, we're going to get to 3. We know 3 is a prime number. If it wasn't, it would have been canceled out. Notice that 6 here is never going to show up, because 6 would have been canceled out. For example, if I hadn't written the 3, if I had actually wrote this as a 2 times 3, that 2 would have canceled this out, and we would have been left with a 5 and a 3. So again, this is just math. We will now take 3 and divide the remainder by 3 as many times as we can. We can only do it a single time, divide the 3, and now we're left with a 5. This is just a technique for us to make sure that we only look at the prime factors. One quick last thing, let's consider the number 2 times 3, which we know is 6. So 6 is this. We will, in our case, iterate from 1, or rather starting from 2 up until the square root of 3, which is going to be 2 point something something. And we're going to take this and round it down, and it's going to end up being 2. So we're going to iterate from 2 to 2 inclusive. We're going to find that, yeah, 2 is a prime factor of 6, and we're going to cancel the 2 out. But we're never going to end up getting to what remains here. We're never going to see the 3. We're never going to consider that 3 is a prime factor with the way that we're coding it up by only stopping at the square root of 6. Once we're done finding all the prime factors up until the square root, we will then look at the remaining number. We canceled out potentially every other prime factor except one number that remains. And if that number ends up being 1, In our previous example where we were looking at 60, we would have canceled that out until it ended up equaling 1. But in this case, we didn't. It doesn't equal 1. It is a number. And if it is a number, we know for sure that it is a prime number. So we would consider that as a factor as well. Otherwise, we won't get all the prime factors of 6. That was a lot of math. I know it's pretty abstract. Unless you've done some studying of factors and prime factorization and stuff, this isn't really going to come naturally to you. So don't feel bad if you weren't able to figure it out. Now we can finally get into the code. So the first thing I'm going to do is just code up our union find class. It's just going to be a utility class that we end up needing. And this isn't going to be any unique from any other union find problem. This is just a bunch of boilerplate, to be honest. So with our constructor, we're going to pass in the number of components. So there's going to be 3 things that we keep track of in union find. We definitely want to know the parent of every single node. At least that's how I kind of refer to it. Here, if we have n components, we will have 0 to n minus 1 parents. Each node will originally have itself as the parent, and we will do union by rank because it's typically more optimal. Initially, we'll say the rank of every single node is just going to be 1. And I guess just to make it a bit more simple, we'll just use the size instead. We also want to maintain the count, the number of components. We know initially it's n, but every time we do a successful union operation, we are going to decrease that by 1. So I will have the union down here, but before we actually implement that, unioning 2 components, we want to have a find method. So given some node, we want to be able to find its root parent. The easiest way to do that is recursively, though I've in the past done a loop for that. This way we can do path compression a bit more easy. So what we're going to check is, does the parent of this current node, is it not equal to itself? Because if it is equal, if these are equal, then what we can do down here is just return itself. We can return self.parent of x. But if they're not equal, we want to find the parent. So we will say self.find of the current value's parent. Starting from there, find its root parent. We're going up the chain basically. And while we're doing this, we might as well do a bit of path compression. So we can say that when you find the root, assign it to this. So the path from here all the way to the root will be a little bit shorter potentially. And then we can actually return the same value we stored in there. We can end up returning it down here. Now for the union, we want to basically find parent of x and parent of y. So let's do that like this. So self.find the root parent of x and self.find the root parent of y. Now, if the parents are equal, that tells us that they are already a part of the same component, in which case we will just return. We could return false if we wanted to indicate whether this was successful or not, but we actually don't need to in this case. We'll just return. But the thing that we do want to keep track of is now, if we are not returning here, we're going to do a union operation. And if we're going to do that, we are going to be decrementing the count, the number of components by 1, because we're merging 2 components together. Here, let's do that merge. If the size of the first component, let's say px, is less than the size of the y component, py, then we're going to take the smaller component and make it a child of the larger component. So this is just a slightly more efficient way to typically do it. So we'll take the parent of px and set it to py. Otherwise, we're just going to do the opposite. So I'll just copy and paste this down here. Py parent will be set to px, and we should probably update the size as well. So the size of py is going to increase by whatever the size of px was. In the other case, it's going to be the opposite. So px and then py here. So this is just a bunch of boilerplate. I've done this so many times that this is actually the easy part of this problem for me. This is a good chance for you, if you're not familiar with this, to practice union find. You could also solve this problem with a DFS or BFS if you really wanted to. So now down here, first, let's actually initialize our union find data structure. We'll initialize it with n components, or the length of nums. That's how many components we'll initially start with. And we're going to go through every number. We're going to keep track of its index as well. So we're going to do it like this: enumerate nums. We'll have the index and the number. And now we want to get all the prime factors of n. We're going to start with f equals 2. I'm actually not going to use a for loop for this because it's a little bit easier to write it this way. It's easier to say if f times f, the square root of the factor, is less than or equal to n, then we continue. If we were doing it with a for loop, we'd have to check that f is less than like the square root of n, and we'd have to like take into account off by 1 errors. We'd have to round this potentially, so it's easier to do it this way. We don't have to round anything. So I'll stick with this. And now we want to know, is this a factor of n? So let's say if n modded by f is equal to 0, it's a factor. So what do? Well, we want to know, was there another number that had this as a factor? Because if there was, we kind of want to do a union, don't we? We want to do a union find dot union the two numbers together. How do we know that? Well, that's what that map I was talking about earlier, that hash map. I'm going to call it factor index. It's going to be a hash map. It's going to map f to the index of a value with that factor f. We don't need to make this a list, remember. We can just keep track of a single one because that's all we need to do union find. And the reason we have the index, again, is because we could have duplicates in num. So when we do union find, we want to union using the index. So now we check if f is in factor index. That means a number that we saw earlier has already been added here. So we want to union the current number, and we're going to use the index I, and the index of the previous number that also had the same factor. So let's say factor index. Let's get the index like this, passing f as the key. So this is what we would do if we already have something in factor index. Otherwise, we are finding a first number with this factor. So let's add it to factor index. Factor index f is going to be equal to I. And there we go. But remember the problem that I kind of talked about. Let's say we have a number 2 times 2 times 3 times 5. We don't want to run into, like, these two numbers combined are also going to be a factor. 2 times 2, 4 is going to be a factor, but it's not a prime factor. So anytime we find a factor, and the first factor we find is always going to be prime by definition. And so when we find a prime factor, we're going to say, while it's divisible by f, while it's a factor, let's go ahead and set n equal to n divided by f. 2 slashes is integer division. There you go. So we're going to basically eliminate that factor as many times as we can. So it's gone now. Now consider the case where we have a number like 2 times 3. We have gotten rid of the 2 factor, but when we get to 3, we're going to find that 3 times 3 is actually not less than or equal to 6. So this loop is going to terminate, but we missed that last factor. So in order to catch it, down here, let's say if n is greater than 1 still, if it's equal to 1, we don't care about 1 as a prime factor. But if it's greater than 1, we're going to do the exact same thing that we kind of did over here. So I'm actually going to copy this. Well, actually, I won't copy it because it's slightly different. So now if n is greater than 1, we want to know if n is in factor index, because then it's a prime number. And it's a prime number that's already been seen. So then we'd say union find dot union, this index I, and whatever the index of that other number was. So using n as the key this time rather than f. And if that's not the case, then we're finding this number for the first time, which is a prime number. So we're going to say factor index of n is going to be equal to 1. This is, again, not trivial at all, but this is pretty efficient. So now down here, we can return true if the number of components is equal to 1. Otherwise, we will end up returning false. And we know count is just a field that we have on our union find structure. So that is pretty much the entire code. One thing I think I forgot over here is we want to increment f by 1 each time. We want to consider every number less than the square root of n. And I unfortunately had a typo here. I don't know why I put a 1 here. We want to map it to the index, which is going to be I for the current number. But that is the entire code. Let's run it to make sure that it works. And as you can see on the left, yes, it does. It's relatively efficient. I will say that the whole prime number nature of this problem, it's relatively unlikely you're going to see something like that on a coding interview. This is a hard problem for a reason, but I think the initial setup of this being a graph problem, whether you solve it with union find or DFS or BFS, I think that actually is a relatively common thing you'll see in interviews. So if you want to learn more about that, you can check out Leetcode.io. Thanks for watching, and I'll see you soon.